for having us. Myself, James Bork, CEO and co-founder of Into.xyz. My CTO, Stephen Mathieson, is also on the call. Originally from Silicon Valley, from the Bay Area, but now living in Paris. So kind of changing the environment a little bit, getting a better sense of kind of the global landscape. We're blockchain guys. We're I don't know how many blockchain folks you guys have joined. Kind of got started in 2016, really as a hobbyist, and then we went full time in 2019, mostly on all the infrastructure that was missing for a lot of these decentralized architectures, access management, data encryption, that kind of thing, and it led us to really focus on multi-party computation. So our first kind of main goal was a lot of research into key storage in a decentralized way, in a way that was kind of acceptable for our community. But that quickly led us into private key generation and private key management. In 2019, a lot of our research was focused on using trusted execution environments in order to more safely perform these computations, but ended up going with multi-party computation in 2021. So our MPC protocol is called the Lisbon Account Protocol. Our company is called Into. At that point, we were traveling a lot backward from Lisbon, so it just kind of made sense. But now that we've kind of concluded our multi-party computation chapter and starting to look at actual customers and actual implementation, we're seeing more and more demand for confidential compute. And so really wanted to take this opportunity today to kind of establish a baseline, at least for us, what MPC is, and then explore from a threat modeling perspective the opportunities to improve multi-party computation using confidential compute. I'm going to do my best to keep this between 20 and 30 minutes, so we won't go too far into the cryptography, but hopefully enough to establish a baseline and hopefully have some decent Q&A towards the end. So at a very high level, multi-party computation, it's the goal is still some kind of an output, but instead of performing this computation on one machine, it's typically performed on multiple devices. These devices are also, at least in our environment, typically controlled by different parties. And then once that computation has been done, the final output is aggregated and then shared amongst the group. The real goal here is to minimize any opportunity for a single point of failure. In our context, our protocols, we strive to be leaderless and trustless, and typically lower the bar, the technical requirements for performing this computation. Some of these limitations, MPC for us really focuses just on key generation and key signature. And this is almost entirely limited to elliptical curve cryptography. So we do a lot of EC DSA and Edwards DSA, a little bit of BLS. We rely very heavily on local compute, but as I mentioned before, no single machine ever does all of the computation. And then probably the largest limitation is that this is really not for general computation, and specifically not for encryption. There has been some good progress in the past couple of years for threshold encryption, particularly kind of within the context of fully homomorphic. But we're kind of right now limited to just key generation and signatures. So as I'd mentioned before, right, our journey kind of started with trusted execution environments. And so we wanted to just kind of start with hardware security and confidential compute and MPC. Are we really looking at substitutes, or are we looking at complements? And so kind of originally, because of the values of decentralized architecture of the blockchain community, we ended up leaning with MPC and really running with that. But the reality is that confidential compute and HSMs do provide a lot of advantages that you simply can't achieve with multi-party computation. It's definitely more mature, right? Practical multi-party computation is only, I'd say, probably 5 or 6 years old. It's also much more sophisticated. You can deploy confidential compute in a much greater variety of applications, from trusted execution environments, Intel SGX and AMD chips, to like the TPMs that are going in everything. And then you got like your enterprise grade HSM. But for MPC, kind of what really led us to it was that we were able to deploy this in a decentralized permissionless, and mostly unsecure environment to still have reliably secure key generation. It's also typically slower. So yeah, so then at the end of the day, even though we went with MPC, we're kind of coming full circle and really starting to look again at using confidential compute to kind of fill out some of our blind spots. Yes, Mike?
Just a quick note. If you go back a slide,
Yes.
um, just so you know, our definition of confidential computing doesn't include TPMs or HSMs. It's specifically TE
Hmm.
based. That's just FYI, really. That's what the consortium's about. Not that those
Okay.
two, not that the other things aren't useful in different ways, but it's not what we count.
Okay, so just to clarify, what is your definition then of confidential compute?
Is the performing protection of data in use using cryptographically attested hardware-based TEs.
Okay, fantastic.
Good job, Mike.
Appreciate
I
it.
should remember it by now. I wrote most of it, and B, it's been around for about 4.5 years now. So,
Well, for us, definitely most of the opportunity is in the hardware security and the protected compute. So that's hopefully we'll stay on topic. Um,
oh, cool.
just just to get this out there for us, like I want to just be completely frank, like what the blockchain is supposed to be and what a lot of blockchains are today, there's a discrepancy there. So for us, it's a peer-to-peer network with a consensus mechanism, and we have incentivizations towards decentralization and greater distribution, again, minimizing single points of failure. For us in particular, the focus was really more on the global computer elements of blockchain computing and not like Bitcoin as digital cash and cryptocurrencies. And so we were really limited by the virtual machines that were around in 2017, right? Limited access to compute, limited access to storage, non-existent access management and data storage. Right, but ideologically driven towards this idea that we should be pushing towards decentralization, reducing concentration, and then you have like all your crypto punk, crypto anarchy, right? Autonomy, privacy, self sovereignty, etc. But again, we're not here to talk about blockchain. So at a high level, MPC, for those that aren't familiar with it, this is kind of how it works. I apologize that the graph is a little bit hard to read, but we start off with verified secret sharing. And in our case in particular, it includes a pre-registration phase. We start with the assumption that you have an address or an identifier for the other participants. The proposer goes ahead and creates a secret and then starts this process of sharing those secrets in a verifiable way in order to create a pool of qualified participants. This pool of qualified participants um, will then share proofs to each other. Typically, this is using some form of a zero knowledge proof, in which if everything checks out, then you know who's supposed to be participating in this protocol and who is not. If someone is there that is not supposed to be there, then we'll go into a dispute resolution phase, in which case you'll actually expose part of that private key. The rest of the community will jump in. And at the end of the day, we'll get to this point where we now have a qualified pool of participants. This qualification is both to share secrets, but also to establish secured channels of communication. In our protocol specifically, we use the blockchain as our bulletin board, effectively, right, as a means of posting and retrieving information from other participants. But if this is like a multi-party computation-based like network service, right, you might be doing other forms of communication. And then ultimately, the output is a shared public address, right? And so everyone will contribute some key material, some public-facing key material to the group. And then once everyone has participated, then anyone can go ahead and aggregate that information. And then you now have a shared public address with multiple participants involved. So it's a very elaborate way of performing a key generation, but again, in a way that strives to reduce single points of failure. But as mentioned earlier, MPC is not a silver bullet. So as we kind of went through our development, once we had a working proof of concept, we did bring on an external auditor for some collaborative threat modeling. So we did a simplified version, a hybrid of stride and dread methodologies that really ended up bringing up kind of three main areas of opportunity to plan for and reduce our attack service for our protocol. And so those are kind of generalized blockchain threats. Specifically, threats within the decentralized key generation process was our most substantial. And then actually using the account, right, in the formation of threshold signatures and how the protocol dictates that. So with the blockchain, there was like a lot of kind of general blockchain problems, including forking, 51% attacks, and Sybil attacks. Some of them were specific to the way that blockchains work, like ordering and memory pools. And a lot of these were also just internet problems, right? DNS hacking, problems with TLS or HTTPS, clickjacking. This is, base threat model stuff. But one of the most substantial risks was actually just in the management of credentials at scale. Just as an example, recently, Solana, one of the major ecosystems, they had a core library, a Web3 JS library that was compromised due to GitHub credentials. And so for 3 updates, they actually were pushing code that was malicious, and people were losing their private keys when they interacted with anything that used this library. And so again, probably a little bit outside of Mike's definition of confidential compute, but an opportunity for better management of credentials definitely exists. Where the rubber really hits the road for us is in this distributed key generation. Because it is so heavily dependent on local computation, any degree of compromise on that local machine obviously introduces a lot of risk to the protocol. And whether that amounts to just bad computation, poor encryption for secret storage, or even bad randomness, right? A lot of the advantage of using a trusted execution environment is that you have reliable randomness. So as an example, if your proposer injects bad randomness into their and results in bad encryption for their secret, every moment then after in the protocol is effectively compromised. When the proposer first begins to create an account and starts this protocol, there's no degree of forward secrecy, right? You can't really introduce ephemeral keys yet. So there's a lot of limits and a lot of risk at that moment. So obviously, just for practicality, we weren't able to mandate the use of trusted execution environments for the distributed key generation. But in the future, and especially within environments that have higher requirements, we definitely see a huge opportunity and starting to get a lot more asks for this. So as an example, like this would be a fairly standard implementation of our protocol, right? You have end users that are participating in the protocol. You also have applications and hosted services that are participating in the protocol. And at any single one of these points, we could leverage at scale trusted execution environments to improve this, right? Whether it's, again, TPMs, if it's the biometrics on your cell phone that you're using to go ahead and log in, to your desktop computer that's participating in this elliptical curve cryptography, or the hosted service itself, which we need for scale to go ahead and use some form of bare metal security, especially in an environment where there's hypervisor risk. We also, right, there's a recovery factor that we've introduced that can use things like hardware wallets, but also use trusted execution environments to go ahead and back that up. And so all of this is, again, very specifically for the computation. There's this kind of much greater factor that encryption doesn't really happen with MPC. And so if we're able to use trusted execution environments as well for the encryption and the communication process, there's a ton more of opportunity kind of in this MPC kind of integration. The last one is threshold signatures. So because there isn't a single party that has a aggregated private key to go ahead and sign with in multi-party computation, we're forced to use threshold signatures. So typically this could be something like 2 out of 3. But it also has a substantial risk because this is the actual use of the account, and specifically in a blockchain environment, this enables you to transfer digital assets and also transfer ownership of this account entirely. And so one of the biggest risks within the threshold signature component of our protocol is the manipulation of the protocol itself and running it, executing this protocol in an unsecured environment. where someone can manipulate either the perception of time, the ordering of the process, or of the deadlines. And so if any of this is changed, you could, inadvertently submit a transaction or perform an action that wasn't actually what you signed, right? We're using a form of blind signing. And so hoping that, using trusted execution environments, we can, further make this process safer. So at the end of the day, the big question is, does confidential compute increase or reduce the attack surface of multi-party computation for decentralized environments? And as you can see here, I think ultimately there's more advantages to using confidential compute than disadvantages, right? We can substantially lower the risk of compromised local devices or hosted services that are participating in the protocol at scale, which is really why we're starting to look at confidential compute. Much stronger protections against hypervisor attacks and compromised hypervisors. So pushing that bare metal security element to it. Better verifiable randomness, better execution, secure execution of critical cryptographic libraries, and better encryption at scale. Some of the pushback that we got early on when we were trying to deploy trusted execution environments for blockchain was this kind of, we call it, I don't know, they refer to it as proof of intel, right? But it's the centralized attestation that's required to spin up and provision your trusted execution environment. Good example of that would be like the MSI compromise from, I think, 2 years ago, where the root master key for a lot of the execution environments was compromised. Then MSI and Lenovo hardware had to be reprovisioned. We also found it difficult in a non-enterprise environment to provision trusted execution environments at scale, right? If you were limited to that device and the sharing and loading of encrypted blobs was limited at the time, this was something that we felt was a shortcoming. And then I think lastly, blockchain uses a lot of non-NIST approved curves. And so we found so far that there's limited support for like P256K curves and things that are commonly implemented in blockchain environments. And it's hard to use these curves or to get these curves introduced into the libraries that are used in trusted execution environments. So at the end of the day, the way we're looking at it is there's really two big opportunities for confidential compute. And we'd love to, again, engage with your community more often and really learn what the state of the art is, specifically for improved security at the enterprise or institutional level. And secondly, for scalability. So obviously, confidential compute helps us minimize the risk of using devices in the wild. We're not doing this in a closed, protected environment. We're talking about someone on the street with their cell phone using their Apple ID to try and interact with a blockchain. The confidential compute element really provides greater controls for MPC and helps reinforce a lot of our blind spots. And then lastly, it's becoming more and more accessible than ever, right? You can't run Windows 11 without the TPM support. Trusted execution environments are everywhere. There's been a lot of great progress in virtual trusted execution environments. I think this is really the opportunity where we have, as multi-party computation and blockchain guys, to learn more. And then secondly, scalability. One of probably the biggest challenge that we're having for deploying multi-party computation at scale in a permissionless way is increasing the availability of participants. And so if you are using a hosted service to go ahead and participate in an account, provisioning these at scale is incredibly difficult for us. Yes, Mike. I think you're still on mute.
Yep, sorry. I was wondering what you meant by virtual TEs. I'm aware of virtual TPMs, but not virtual TEs, and I have concerns.
You have concerns. I mean, I know that this was research that was coming up a few years ago, and I haven't checked in recently to see where it was, but it was, I think, largely backed by AMD. I'd have to pull it up. But it was an opportunity to, yes, Alec, please join in if other people know more about this.
No, I was gonna set up the next question after this answer, so please.
Okay.
Yeah.
Yeah, I mean,
I
virtual TPMs makes lots of sense. Virtual T's is kind of the opposite of sense if it's not hardware based,
right.
because you lose your root of trust completely and you've lost the isolation that you have with hardware.
I don't think it had a lot of adoption. It might have been dropped altogether. But back when we were doing our research into trusted execution environments, I'd have to pull up the links. It's been a minute. But there was
Yeah,
talk
someone's
of,
found one.
Yeah, let's not
Okay.
rat hole on it. It's sort of a passing thought, I think. So
Yeah, sure.
he's
Okay,
mentioned,
that's fine. Let's carry on. Thanks for the Stephen for providing a link.
okay,
Yeah, so going to what you were talking about earlier, and some of the diagrams went by a little quickly, and maybe I didn't follow exactly right. But
sure.
we're a hyperscaler, right? I'm with Microsoft Azure. So what
Yep.
our business is providing confidential computing Ts using chips from our other friends on this call, Intel and AMD, notably today, to actually produce trusted execution environments in the public cloud. You say
Yep.
that you use a lot of local compute, and just kind of want to get you to riff on the idea of where there's that boundary line where you're required to use local compute for the benefits that you get, and that the need for trusted execution environments in local compute so that you have some guarantee of actual randomness and other things, where that dividing line might melt away and allow you to use public infrastructure if we had confidential computing in public clouds.
Right. So probably this is likely the diagram that you're referring to. So in order to like the original version of the protocol really focused on end users controlling all of their factors, right? Like the most basic integration would be myself as an individual has my mobile phone using a single sign-on, let's say a crypto browser-based wallet that can provide an additional signature, and then a backup using some form of hardware security, right? Like we were designing for blockchain. This was kind of our original intention. So your Ledger, your MetaMask, and your Google. Ta-da. I've got my three factors. I've got my account. I now have enabled account recovery, shared ownership, distributed risk, all these benefits of using multi-party computation in a decentralized architecture. What we found as we kind of kept pushing to try and find better use cases is that the level of convenience that the account had was substantially reduced because you have an individual that at minimum needs two-factor authentication. And so we ended up developing a version of our SDK that was meant to operate as a cosigner, right? So it's consistently listening for opportunities to provide a partial signature that was user initiated. And so that really kind of unlocked a lot of doors for us when it came to scale. It also allowed organizations to start providing greater controls over the account, right? So you could deploy this in an enterprise environment, and rather than have it be quote unquote self custody, it actually results in being a shared custody or permissioned access because the organization would maintain 2 out of 3 of the key shares, and the end user would only have one key share to go ahead and initiate the use of the account. So that was all good and well, and now that we're really pushing more towards scale, there's limitations as to provisioning these cosigners, right? Like it's right now it's a hosted service. And the fact that every cosigner only has the cryptographic key material for the accounts that it participated in, right, means that you have to be reliably be able to provision these machines to go ahead and participate in these accounts. And so that's something that we've recently started to explore. Right, just how do we really distribute this load and kind of balance the requirements to perform MPC in this permissionless way at scale? And it's been challenging so far, right? To be able to consistently get that key material in a hosted service that's able to quickly participate in this and then deprovision almost immediately. So it's something that we're pushing towards, and part of why we're here is to learn more and start getting in touch with the right experts to figure out what's the best way to really solve this problem for people that want to use our protocol.
Got it. When you're provisioning, you speak of having to provision massive numbers of machines at scale. You're comfortable doing that in hyperscalers. It's not a provisioning of machines where you control the physical hardware.
Right. And I guess just to further elaborate, we are like our protocol and our SDK, it's freely distributed. We don't do integrations at this point. What we're really looking to do is support the needs of people that are building on our protocol. And so for some of our more enterprise focused users, right, hyperscalers it's mandatory, right? And they're struggling to figure out how to use both KMS systems and confidential compute systems in order to deliver the scale that they need, right? Not talking tens of thousands like most blockchain projects, but looking at millions of requests on a regular basis. Cool. All right. Well, we front ran the Q&A a little bit. The last thing was scalability. So Alec, thank you. I think that ties in pretty close. Provisioning at scale. The other kind of complication with this is that with multi-party computation, in order to carry out one action, you need at least, at minimum, 2 signatures. And so you end up getting a lot of participants doing a lot of things for just one result, for one output, which means that, right, you're scaling depending on how many people are participating in these accounts. And then, just enabling enough of these cosigners and making sure that they're available in a way that's reliable and efficient without compromising on security is probably the biggest opportunity for us with confidential compute. So yeah, ta-da. Thanks, guys.
All right, well, that was great and very efficiently done, James. So I know we grabbed a couple questions along the way. I see there's at least one more set in chat from Alice. And Fritz has his virtual hand virtually raised.
Cool.
I'm
Why don't we
also
go with
standing
Fritz?
here like this. Should I go first? I can also go second if you're free to.
Alice, would you
first.
like to read your question, or you want me to read it for you? I'll just read Alice's question in case she can't come off mute here. What's the cost implications in terms of compute resources? And secondly, are there trade-offs? Are we giving away throughput for security? I assume it's parallel computing since it's multi-party, right? How scalable is this solution?
Yeah. So cost implications in terms of compute resources. This is one of the major reasons that we focused primarily on local compute. All of the heavy lifting for us happens off chain. And so for us, that was substantially less expensive than trying to use a distributed virtual machine to do any of this. The trade-offs for us was definitely inconvenience and inefficiency, right? It takes longer to form a threshold signature than it does to just grab a private key and do an elliptical curve signature. The parallel computing bit, the multi-party computation, we actually go through several rounds of communication. I think, and my CTO would have to lean in on this one. I think we're doing 3 rounds of communication. And so it's not really parallel computing. One of the kind of advantages of our protocol is that it's asynchronous, right? It's designed for decentralized architectures. And so you can find faster multi-party computation in a permissioned system where you have greater controls over the different nodes, the different signers, and the channels of communication, right? You can reduce that latency that might enable parallel computing. But really it's more of it's an asynchronous process. I think that covers it. Alice, did that answer your question? I know your network is terrible.
Sounds like it
Cool.
did.
Okay,
Thank you.
excellent.
All right, Fritz, you're up.
So sorry if you answered this a little bit already, but maybe I want to bring that point home. So what now that you introduced TEEs to the mix, right, into the threat model, what pieces of MPC do we even still need, and can we not do many of them with TEEs nowadays? And I'm asking this not because I do like MPC, but whenever I thought about a mix of MPC and TEEs, I very quickly had the feeling that they just have contrary threat model assumptions. And once you have one, you don't need the other anymore, which doesn't mean either of them is useless, but combining them, I so far very quickly had a slump or encountered a slump and thought, well, then I can just drop the MPC if I'm already like trusting the CPU to do this thing. So
Sure.
yeah, go ahead.
So I really think the advantage of multi-party computation is in I'm going to say we're trying, it's in an attempt to remove single points of failure, right? And that was the pushback that we got early on from the blockchain community, right? 2018, 2019 was this idea that, centralized attestation and root keys, master keys that then provisioned, right, using like a HD cryptography, heuristic, deterministic, creation of keys, that would put the entire system at risk if this single point of failure was compromised. Like an unusual fallout of that MSI master key being compromised a few years ago, there was one of the, I guess, victims in this case. There was a blockchain network called Secret Protocol that they were doing trusted execution environment nodes, and is basically TE plus blockchain, and their entire network was compromised for a matter of months because the master private key that was used to provision all of the trusted execution environments was part of that attack. It was leaked. Had they been using, again, multi-party computation in addition to trusted execution environments, it would have lowered the chances for that to happen, right? And not like distributed computation is by no means perfect. We've seen a lot of issues with like governance and just in general, like people not using good key hygiene for distributed systems. But by combining them for us, that's super, super helpful. The second bit that I didn't touch on in this presentation, and one of the major advantages of multi-party computation and the way that we're performing elliptical curve cryptography, is that once you've established a baseline and once you've established this public address, you can in perpetuity use a process called key resharing to go ahead and recombine key material and then redistribute it, effectively choosing additional points along the curve to go ahead and issue new key shares, right? New individual parts of key shares to the participants without changing the static permanent public address, right? So if you have a collection of devices, if we're using this at scale, right, using a hyperscaler, you can maintain the same public address for all of these services, but on a regular and frequent basis, rotate the security credentials without compromising its ability to form a valid signature against the public address. So this idea of a dynamic private key material that is also distributed at scale is really one of the stronger advantages of multi-party computation. And just being able to do that securely with trusted execution environments for us means that we can do this for longer periods of time safely at a greater scale. I hope that at least answered part of your question.
Yeah, it does. And Dennis already saying we might want to move on.
Okay.
Do you have a second to elaborate on the root key loss that you mentioned? So is that something you just remember, or was there something concrete? Because
it was something concrete.
Mm-hmm.
I'll look it up after the.
Kind of
I'll look it up after
on something that's okay. Go ahead.
I'll look up the incident as soon as I'm off, and I'll go ahead and post it in the chat.
Yeah, great. If you remember, no worries. I mean, also like not trying to push you on something that you just remember.
No.
Right?
It was,
but just interesting to hear about what has been seen from your end.
Yep. Let me go ahead and find it.
Awesome. Yeah. Thanks for the talk. Thank you.
Okay.
All right. Thanks so much for the talk, James.
All right. Thank you, everyone.